skin effect is the tendency of an alternating electric current to become distributed within a conductor such that the current density is largest near the surface of the conductor, and decreases with greater depths in the conductor. The electric current flows mainly at the skin of the conductor, between the outer surface and a level called the skin depth. The skin effect causes the effective resistance of the conductor to increase at higher frequencies where the skin depth is smaller, thus reducing the effective cross-section of the conductor. The skin effect is due to opposing eddy currents induced by the changing magnetic field resulting from the alternating current. At 60 Hz in copper, the skin depth is about 8.5 mm. At high frequencies the skin depth becomes much smaller. Increased AC resistance due to the skin effect can be mitigated by using specially woven Litz wire. Because the interior of a large conductor carries so little of the current, tubular conductors such as pipe can be used to save weight and cost. Conductors, typically in the form of wires, may be used to transmit electrical energy or signals using an alternating current flowing through that conductor. The charge carriers constituting that current, usually electrons, are driven by an electric field due to the source of electrical energy. An alternating current in a conductor produces an alternating magnetic field in and around the conductor. When the intensity of current in a conductor changes, the magnetic field also changes. The change in the magnetic field, in turn, creates an electric field which opposes the change in current intensity. This opposing electric field is called counter-electromotive force. The back EMF is strongest at the center of the conductor, and forces the conducting electrons to the outside of the conductor, as shown in the diagram on the right. An alternating current may also be induced in a conductor due to an alternating magnetic field according to the law of induction. An electromagnetic wave impinging on a conductor will therefore generally produce such a current. This explains the reflection of electromagnetic waves from metals. Regardless of the driving force, the current density is found to be greatest at the conductor's surface, with a reduced magnitude deeper in the conductor. That decline in current density is known as the skin effect, and the skin depth is a measure of the depth at which the current density falls to 1/e of its value near the surface. Over 98% of the current will flow within a layer 4 times the skin depth from the surface. This behavior is distinct from that of direct current, which usually will be distributed evenly over the cross-section of the wire. The effect was first described in a paper by Horace Lamb in 1883 for the case of spherical conductors, and was generalized to conductors of any shape by Oliver Heaviside in 1885. The skin effect has practical consequences in the analysis and design of radio frequency and microwave circuits, transmission lines, and antennas. It is also important at mains frequencies in AC electrical power transmission and distribution systems. Although the term skin effect is most often associated with applications involving transmission of electric currents, the skin depth also describes the exponential decay of the electric and magnetic fields, as well as the density of induced currents inside a bulk material when a plane wave impinges on it at normal incidence. Formula: the AC current density J in a conductor decreases exponentially from its value at the surface Js according to the depth d from the surface, as follows, where delta is called the skin depth. The skin depth is thus defined as the depth below the surface of the conductor at which the current density has fallen to 1/e of Js. The general formula for the skin depth is where equals resistivity of the conductor equals angular frequency of current equals 2 pi times frequency equals relative magnetic permeability of the conductor equals the permeability of free space equals relative permittivity of the material equals the permittivity of free space equals at frequencies much below the quantity inside. The large radical is close to unity, and the formula is more usually given as This formula is valid away from strong atomic or molecular resonances and at frequencies which are much below both the material's plasma frequency and the reciprocal of the mean time between collisions involving the conduction electrons. In good conductors such as metals, all of those conditions are ensured at least up to microwave frequencies, justifying this formula's validity. For example, in the case of copper, this would be true for frequencies much below 1018 Hz. However, in very poor conductors, at sufficiently high frequencies, the factor under the large radical increases. At frequencies much higher than it can be shown that the skin depth, rather than continuing to decrease, approaches an asymptotic value. This departure from the usual formula only applies for materials of rather low conductivity and at frequencies where the vacuum wavelength is not much larger than the skin depth itself. For instance, bulk silicon is a poor conductor and has a skin depth of about 40 meters at 100 kHz. However, as the frequency is increased well into the megahertz range, its skin depth never falls below the asymptotic value of 11 meters. The conclusion is that in poor solid conductors such as undoped silicon, the skin effect doesn't need to be taken into account in most practical situations. Any current is equally distributed throughout the material's cross-section regardless of its frequency. Resistance. The effective resistance due to a current confined near the surface of a large conductor can be solved as if the current flowed uniformly through a layer of thickness delta based on the DC resistivity of that material. The effective cross-sectional area is approximately equal to delta times the conductor's circumference. Thus a long cylindrical conductor such as a wire, having a diameter d large compared to delta, has a resistance approximately that of a hollow tube with wall thickness delta carrying direct current. The AC resistance of a wire of length L and resistivity is. The final approximation above assumes a convenient formula for the diameter dW of a wire of circular cross-section whose resistance will increase by 10% at frequency f is. The increase in AC resistance described above is accurate only for an isolated wire. For a wire close to other wires, e.g., in a cable or a coil, the AC resistance is also affected by proximity effect, which often causes a much more severe increase in AC resistance. Material effect on skin depth. In a good conductor, skin depth is proportional to square root of the resistivity. This means that better conductors have a reduced skin depth. The overall resistance of the better conductor remains lower even with the reduced skin depth. However, the better conductor will show a higher ratio between its AC and DC resistance when compared with a conductor of higher resistivity. For example, at 60 Hz, a 2000 mcm copper conductor has 23% more resistance than it does at DC. The same size conductor in aluminum has only 10% more resistance with 60 Hz AC than it does with DC. Skin depth also varies as the inverse square root of the permeability of the conductor. In the case of iron, its conductivity is about 1/7 that of copper. However, being ferromagnetic, its permeability is about 10,000 times greater. This reduces the skin depth for iron to about 1/38 that of copper, about 220 micrometers at 60 Hz. Iron wire is thus useless for AC power lines. The skin effect also reduces the effective thickness of laminations in power transformers, increasing their losses. Iron rods work well for direct current welding, but it is impossible to use them at frequencies much higher than 60 Hz. At a few kilohertz, the welding rod will glow red hot as current flows through the greatly increased AC resistance resulting from the skin effect, with relatively little power remaining for the arc itself. Only non-magnetic rods can be used for high-frequency welding. At 1 MHz, the skin effect depth in wet soil is about 5.03 meters, in seawater it's about 0.25 meters. Mitigation. A type of cable called Litz wire is used to mitigate the skin effect for frequencies of a few kilohertz to about 1 megahertz. It consists of a number of insulated wire strands woven together in a carefully designed pattern, so that the overall magnetic field acts equally on all the wires and causes the total current to be distributed equally among them, with the skin effect having little effect on each of the thin strands. The bundle does not suffer the same increase in AC resistance that a solid conductor of the same cross-sectional area would due to the skin effect. Litz wire is often used in the windings of high-frequency transformers to increase their efficiency by mitigating both skin effect and proximity effect. Large power transformers are wound with stranded conductors of similar construction to Litz wire, but employing a larger cross-section corresponding to the larger skin depth at mains frequencies. Conductive threads composed of carbon nanotubes have been demonstrated as conductors for antennas from medium wave to microwave frequencies. Unlike standard antenna conductors, the nanotubes are much smaller than the skin depth, allowing full utilization of the thread's cross-section, resulting in an extremely light antenna. High voltage, high current overhead power lines often use aluminum cable with a steel reinforcing core. The high resistance of the steel core is of no consequence since it is located far below the skin depth where essentially no AC current flows. In applications where high currents flow, solid conductors are usually replaced by tubes, completely eliminating the inner portion of the conductor where little current flows. This hardly affects the AC resistance, but considerably reduces the weight of the conductor. The high strength but low weight of tubes substantially increases span capability. Tubular conductors are typical in electric power switchyards where the distance between supporting insulators may be several meters. Long spans generally exhibit physical sag, but this does not affect electrical performance. To avoid losses, the conductivity of the tube material must be high. In high current situations where conductors may be between 5 and 50 mm thick, the skin effect also occurs at sharp bends where the metal is compressed inside the bend and stretched outside the bend. The shorter path at the inner surface results in a lower resistance, which causes most of the current to be concentrated close to the inner bend surface. This will cause an increase in temperature rise in that region compared with the straight area of the same conductor. A similar skin effect occurs at the corners of rectangular conductors, where the magnetic field is more concentrated at the corners than in the sides. This results in superior performance from wide thin conductors, e.g., ribbon conductors, where the effects from corners is effectively eliminated. It follows that a transformer with a round core will be more efficient than an equivalent rated transformer having a square or rectangular core of the same material. Solid or tubular conductors may be silver-plated to take advantage of silver's higher conductivity. This technique is particularly used at VHF to microwave frequencies where the small skin depth requires only a very thin layer of silver, making the improvement in conductivity very cost-effective. Silver plating is similarly used on the surface of waveguides used for transmission of microwaves. This reduces attenuation of the propagating wave due to resistive losses affecting the accompanying eddy currents. The skin effect confines such eddy currents to a very thin surface layer of the waveguide structure. The skin effect itself isn't actually combated in these cases, but the distribution of currents near the conductor's surface makes the use of precious metals practical. Although it has a lower conductivity than copper and silver, gold plating is also used, because unlike copper and silver, it does not corrode. A thin corroded layer of copper or silver would have a low conductivity, and so would cause large power losses as the majority of the current would still flow through this layer. Note: the heat-dependent manufacturing process for wire results in oxidation of the surface in the finished product. Therefore, the conductivity of the skin is significantly less than the underlying unoxidized base metal. It is to be expected that unless the oxidized surface material is removed, some loss of performance from the theoretical model will occur. Examples. We can derive a practical formula for skin depth as follows, where the skin depth in meters, the relative permeability of the medium, the resistivity of the medium in omega m, also equal to the reciprocal of its conductivity. The frequency of the current in Hz. Gold is a good conductor with a resistivity of 69922440000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 times 10⁻8 ohms m and is essentially non-magnetic. 1. So its skin depth at a frequency of 50 Hz is given by lead. In contrast, is a relatively poor conductor with a resistivity of 69932200000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 times 10⁻7 ohms m, about 9 times that of gold. Its skin depth at 50 Hz is likewise found to be about 33 mm, or times that of gold. Highly magnetic materials have a reduced skin depth owing to their large permeability, as was pointed out above for the case of iron. Despite its poorer conductivity, a practical consequence is seen by users of induction cookers, where some types of stainless steel cookware are unusable because they are not ferromagnetic. At very high frequencies, the skin depth for good conductors becomes tiny. For instance, the skin depths of some common metals at a frequency of 10 GHz are less than a micrometer. Thus, at microwave frequencies, most of the current flows in an extremely thin region near the surface. Ohmic losses of waveguides at microwave frequencies are therefore only dependent on the surface coating of the material. A layer of silver 3 micrometers thick evaporated on a piece of glass is thus an excellent conductor at such frequencies. In copper, the skin depth can be seen to fall according to the square root of frequency. In engineering electromagnetics, Haight points out that in a power station a bus bar for alternating current at 60 Hz with a radius larger than 1/3 of an inch is a waste of copper, and in practice, bus bars for heavy AC current are rarely more than half an inch thick except for mechanical reasons. Skin effect reduction of the self-inductance of a conductor. Refer to the diagram below showing the inner and outer conductors of a coaxial cable. Since the skin effect causes a current at high frequencies to flow mainly at the surface of a conductor, it can be seen that this will reduce the magnetic field inside the wire, that is, beneath the depth at which the bulk of the current flows. It can be shown that this will have a minor effect on the self-inductance of the wire itself. See Skilling or Haight for a mathematical treatment of this phenomenon. Note that the inductance considered in this context refers to a bare conductor, not the inductance of a coil used as a circuit element. The inductance of a coil is dominated by the mutual inductance between the turns of the coil, which increases its inductance according to the square of the number of turns. However, when only a single wire is involved, then in addition to the external inductance involving magnetic fields outside of the wire as seen in the white region of the figure below, there is also a much smaller component of internal inductance due to the magnetic field inside the wire itself, the green region in Figure B. In a single wire, the internal inductance becomes of little significance when the wire is much longer than its diameter. The presence of a second conductor in the case of a transmission line requires a different treatment, as is discussed below. Due to the skin effect, at high frequencies the internal inductance of a wire vanishes, as can be seen in the case of a telephone twisted pair below. In normal cases, the effect of internal inductance is ignored in the design of coils or calculating the properties of microstrips. Inductance per length in a coaxial cable. Let the dimensions A, B, and C be the inner conductor radius, the shield inside radius and the shield outer radius respectively, as seen in the cross-section of Figure A below. For a given current, The total energy stored in the magnetic fields must be the same as the calculated electrical energy attributed to that current flowing through the inductance of the coax. That energy is proportional to the cable's measured inductance. The magnetic field inside a coaxial cable can be divided into 3 regions, each of which will therefore contribute to the electrical inductance seen by a length of cable. The inductance is associated with the magnetic field in the region with radius, the region inside the center conductor. The inductance is associated with the magnetic field in the region between the 2 conductors. The inductance is associated with the magnetic field in the region inside the shield conductor. The net electrical inductance is due to all 3 contributions, is not changed by the skin effect, and is given by the frequently cited formula for inductance L per length D of a coaxial cable. At low frequencies, all 3 inductances are fully present so that at high frequencies, only the dielectric region has magnetic flux, so that most discussions of coaxial transmission lines assume they will be used for radio frequencies, so equations are supplied corresponding only to the latter case. As the skin effect increases, the currents are concentrated near the outside of the inner conductor and the inside of the shield. Since there is essentially no current deeper in the inner conductor, there is no magnetic field beneath the surface of the inner conductor. Since the current in the inner conductor is balanced by the opposite current flowing on the inside of the outer conductor, there is no remaining magnetic field in the outer conductor itself, where only contributes to the electrical inductance are these higher frequencies. Although the geometry is different, a twisted pair used in telephone lines is similarly affected. At higher frequencies, the inductance decreases by more than 20%, as can be seen in the following table. Characteristics of telephone cable as a function of frequency. Representative parameter data for 24-gauge PIC telephone cable at 21 degrees Celsius. More extensive tables and tables for other gauges, temperatures and types are available in Reeve. Chen gives the same data in a parameterized form that he states is usable up to 50 MHz. Chen gives an equation of this form for telephone twisted pair.